So on page 88, we get into the Taylor series. This is where we, instead of limiting it at a certain number of terms of a polynomial, we just go out forever. Right? So it's infinite series. And we know how to evaluate infinite series, so this is going to kind of tie things together. It has a lot of similarity in terms of approach, but we have that extra step of having to come up with a general term. All right, so let's go through an example, and then we'll talk about the cases that you got to know, or at least be familiar with, for Maclaurin's series of 3 special cases. All right, but let's focus on e to the 5x for now, centered at a equals 2. All right, so f of x, it says give the first 4 non-zero terms, so that's going out to the third derivative. All right. All right, so if I evaluate this by plugging in a 2, I get e to the 10th. All right, but actually, let me just do the derivatives first before I go too crazy with evaluating. All right, so e to the 5x, 5e to the 5x. The next one would be 25e to the 5x, but I'm going to write that as 5 squared e to the 5x. And then 5 to the third e to the 5x. All right, so when I evaluate f of 2, f prime of 2, double prime of 2, triple prime of 2, my equal signs are going off the rails here. I get e to the 10th, 5e to the 10th, 5 squared e to the 10th, and 5 cubed e to the 10th. All right, we have a consistency, or consistent relationship between the derivative and the power of 5, so that's nice. E to the 10th is e to the 10th every step of the way, so even better. All right, so if we write the polynomial, so we're only going out to four terms, but that's piece 3 of x. It would be e to the 10th plus 5e to the 10th over 1 factorial. Now it's centered at 2, so x minus 2 to the first plus 5 squared e to the 10th over 2 factorial, x minus 2 to the second plus 5 cubed e to the third, helps to write e to the third, e to the 10th over 3 factorial, x minus 2 to the third. There was a third in there, I just didn't put it in the right place. All right, so based off of the notation here, we want our summation to follow this form. N equals 0 to infinity, all right, because the nth term represents the nth derivative. There is a 0th derivative, so we want to start it at 0 at the n value of 0. All right, so we have the 0th derivative, 0 factorial, that consistency there. All right. In the numerator, we're going to have the derivative evaluated appropriately. We'll have our factorials, but then from there, it's all particular to the problem. All right, so my general term, if we look at everything that makes up our expansion here, you see that consistency that develops, right? We have an x minus 2 in every case, all right? It varies what power it's being raised to, but let me just write x minus 2. We have an e to the 10th, all right? Now, as far as the coefficient of e to the 10th is concerned, we have a 5, but that could be thought of as 5 to the first. We have a 1, but that could be thought of as 5 to the 0th. 5 to the 0th, first, second, third, and so on. All right? If I want to have a summation that starts off at n equals 0 and goes on and on forever, that would make sense if I were to say 5 to the nth power. All right. Now, similarly, for the power of the binomial, you see that that's always the same as the power of the 5. So that's also going to be raised to the nth power. Now, the only thing left is the factorial. That's n factorial. The justification there is, well, I don't have an n factorial, in fact, or I'm sorry, a factorial for that first term, but that could be thought of as 0 factorial because 0 factorial is equal to 1. So even that now follows the progression of 0 to 1 to 2 to 3. So this would be over n factorial. And that would be the general term. All right, this is the general term. Writing it in this form gives us the entire series. All right, I always kind of look at it as, why do one without the other? All right, but what we would do here, copy, is instead of saying p sub 3, we would say p sub n, and we'd say plus dot 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 right on out to the general term. If it'll let me. There we go. Which then in turn equates to this, which is p sub n of x. All right, so it's definitely a different way of doing it, different than what we had been doing before in terms of evaluating expressions and so on. But now we have a way of representing an exponential or transcendental function using something that's polynomial based. Now, depending on our level of accuracy, the desired level of accuracy, we may or may not have a whole, bunch of work to do. All right, so looking at the Maclaurin cases, we'll start off with e to the x. So f of x is e to the x. F to the nth of x is also e to the x. At 0 is 1. For everything, the original function and all derivatives. So when it comes to developing our polynomial, I would start off with the derivative, 1 over 0 factorial, so the 1 being the derivative value, x to the 0th. So I'm putting all the bells and whistles in here because I want to be able to come up with a general term out of this, plus 1 over 1 factorial x to the first plus 1 over 2 factorial. It's the beauty of that derivative never changing. It goes a lot quicker. 2 factorial plus 1 over 3 factorial x cubed. Now, if I want to come up with the nth term, that's not hard here because you see here that for my 0th derivative, I have zeros, right? So that's consistent with the summation where n starts at 0 and goes to infinity. All right. So if my initial value, my exponents and my factorials and all that good stuff has a 0 in it, or is comprised exclusively of zeros, then you're in good shape. It's a nice place to start. All right. Now I do see that I have consistently a 1 and an x. All right, those denominator values, they start at 0 factorial and then they increase from there. That's consistent with n going from 0 to infinity, so I can call that n factorial. The exponents do the same thing, so I could say it's raised to the nth power. So my summation representing this polynomial would be 1 over n factorial x squared. All right, you can see it follows the progression in the Taylor series. If a is equal to 0, it's nice and easy. All right, so what I can do is I could just say that this whole thing is equal to this. Actually, I'll just slide it over, and now we have a new rule. All right, now we do need to go an additional step here, and that step involves identifying the domain of the series expansion. All right, so for that we need to explore, or not really explore, I guess, more like review some of the series tests in order to help us understand which one would make the most sense here. All right. But I am going to schmidge this in here because we have a relationship. We just need to know the domain. So to understand this, I wanted to bring us back to the ratio test. Okay? Because what would happen is we would need, in order for the series to really converge in the way that we want it, let me just kind of bring it back to what we're looking at here. So we essentially need e to the x to be equivalent to this series, but basically what that means is, in general terms, this series needs to converge onto a function that's modeled by e to the x for all values of x. I'm clicking the wrong way. All right, so in order for a series to converge in a ratio test format, which this does appear to be, this has the look of a ratio test. So I'll rewrite it just so that it stands out a little bit more. N equals 0 to infinity of x to the nth over n factorial. We would need to make sure that the limit as n approaches infinity of this of the ratio that we're going to generate by figuring out a sub n plus 1 divided by a sub n, that limit as n approaches infinity has to be less than 1. All right, and whatever values that allow for that to occur would be our domain. All right, so let's get our a sub n. So this whole thing is our a sub n. Let's get our a sub n plus 1. So x to the n plus 1 over n plus 1 factorial, which we learned previously we're going to rewrite as x to the nth times x over n plus 1 times n factorial. That's going to facilitate cancellation. All right, so it's going to be the ratio of that's not a marker, that, and x to the nth over n factorial. We're finding the limit as n approaches infinity of that. All right, so nice cancellations here. Really, the challenging stuff canceled out, which is great. It doesn't always happen, but when it does, it's a beautiful thing. All right. So this is limit as n approaches infinity of x over n plus 1. That's got to be less than 1. All right. Now, we know that there will be plenty of instances in which this will diverge, but we need it to converge, right? So it's really just a question of thinking about, at least at this point, thinking about under what instances would we have a limit that converges. We want, really, the power on the top to be less than the power on the bottom, right? Because it's going out to infinity. We use our horizontal asymptote rules. Now, one thing you might notice is that x is irrelevant to the limit. It doesn't have an n in it. And it can be factored out. So limit as n approaches infinity, and I'm going to write this as the absolute on the outside of 1 over n plus 1 that's going to go to 0. So x times 0 less than 1, that's saying that all values of x are going to work, because it doesn't matter what x is, it's getting multiplied by 0. It's going to give you a value that is 0, which is therefore less than 1. All right, so therefore this will be true for all values of x going from negative infinity to infinity, which is great. That tells us that we can use this series in lieu of exponential e whenever we want. That's why it says there are 3 special Maclaurin series that you must know. Okay? It's a truth that always is in existence. Right? It goes from negative infinity to infinity. We could always use it. It's good stuff.